So we were talking about mean curvature last time, and let's talk some more about mean curvature. I mentioned that mean curvature comes up in the first variation of area, and so let's go ahead and prove that real quick. And the calculation is carried out in the book. And you remember we had this whole elaborate. And so, what is the statement, first of all? What am I about to prove? So we call this the first variation of area. And so here's the picture. You have some surface. And it has some area. And I want to know how the area changes when I flow in this direction here, eta. Okay, so eta is the speed of the perpendicular flow. We might call it perpendicular speed. Perpendicular speed. And so it's going to be faster in some places and slower in other places, right? Now we also have something called u, right? This is the thing that's length 1. That's the unit normal going out, right? And just to give some examples, if you take a sphere of radius r, and we have u pointing out, then we computed that h is equal to negative 2 over r. Is that correct? Did I get really it's the sign. No, wait a second. Sorry. It's negative 1 over r, right? The principal curvatures are equal to 1 over r. And with that convention, I think we computed the mean curvature to be negative 1 over r. Am I right? Each of the principal curvatures are negative 1 over r. So the average is that, and the product is 1 over r squared. Does that agree with everything we've done so far? I think so. I like to always give an example because it helps me remember the conventions, like what's negative and what's positive. Now you might say, well, why don't we have u pointing in on the sphere? Or you could, and then h would be 1 over r. Okay? Because remember, when you switch the sign of u, if I replace u with minus u, then the shape operator changes by a sign. So then the eigenvalues of the shape operator change by a sign. And so then the average of the eigenvalues changes by a sign. So this h thing is really only defined up to a sign. But, I mean, it has, what it really is, though, it's like that's what the mean curvature is with respect to that normal. Now, when we do a flow, the question is the flow going in the same direction as u? Like, for example, is eta the speed going in the direction of u, or is it the speed going in the direction opposite u? Right? So we have to be clear about that, right? And we're going to say that eta is the speed going in the direction of u. So if eta is negative, that means the surface would be flowing in. You guys get the idea? We have to establish that convention, what positive eta means. And so what we're about to prove is that if we let, so really what we're going to do is we're going to find a family of surfaces, right? So imagine you have your original surface here. Let's see here. M. So we'll call this first surface here M 0, okay? I'm putting the 0 of pi because I think that's what the book does. And then more generally, we're going to get a family of surfaces, okay? And so that next surface there might be M1. And then more generally, we're going to have a family of surfaces here. We might call these M superscript T. Okay? So everybody get the idea? And so what we have is a family of surfaces, a one-parameter family of surfaces. T goes between plus or minus epsilon, or plus or minus k. It doesn't matter. It's defined in some interval that includes 0. Okay? M0 is our original surface. And so that means, now what are we going to prove? We're going to prove that, so we'll let, first of all, A of t will equal the area, the total surface area of M superscript t. And what we want to prove is that A prime of 0 is equal to the integral over M0 of minus twice the mean curvature of the surface times eta times the area form. Okay. And A of t is the area of m of t, but let me also write it another way. A of t is the integral over m sub t of just dA. Okay, I just want to remind you that dA is the thing you integrate to get the area. Okay, that's its definition. And you've done multivariable calculus before. You've computed surface areas before. Anyway, whatever it is that you were integrating to get area, that's what dA is. Okay, and we'll be computing here in just a second. And by the way, more generally, even though we're just going to prove this for t, I mean, we'll prove it for t equal to 0. But once you prove it for t equals 0, notice there's no t's over here. So actually, what we'll find out is that this is actually true for all t. So I can replace this and put a t there if I want. Okay, it's actually true for all t. But then this becomes the mean curvature of mt, of course, and that's the flow speed on mt, right? And that's the area form on mt, right? So with that lost generality, sometimes it's more convenient. Let's just prove it for t equal to 0, and then obviously it follows for all t. Okay. And now what is, so this is the claim, and now we want to do the proof. Okay. Now what follows here is a messy calculation. It's kind of medium messy. It could be worse, I suppose. But when you see it, you're like, ah, really? It could be worse? Seems pretty bad. It's a kind of a tolerance thing you build up here. I mean, first of all, but before we get into the messy calculation of how we do the first variation of area, can we agree that this is fundamental? I mean, all we're doing is trying to figure out the rate of change of the area with respect to some flow, right? I mean, this is obviously fundamental, right? I mean, if you can't do this, then you're basically saying can't do calculus with geometry, right? That's pretty much a confession that I don't know how to combine geometry and calculus. Am I right? I mean, computing the rate of change of area. Like, think of something simpler than that, more fundamental. It involves both, curved geometry. I'm not talking about, no, so beyond triangles, circles, and squares, right? Geometries of surfaces, right? And calculus, right? It's hard to think. I mean, okay, to compute the rate of change of the volume, that's just the shell method, right? I mentioned that last time. Integral of v prime of t is just the integral of a to dA, right? Okay, so this is sort of like our first sort of kind of interesting calculation. And therefore, because it's so fundamental, it deserves patience, right? And let's just do whatever amount of work we have to do. Okay, so how do we do this? And this is actually, what I'm about to show you are some fundamental ideas, just because you use them so much. You use it in, what the ideas we're going to use here are used in variational theory when you compute the first variation of anything. And also it comes up in calculus of variations, some of these ideas, okay? And I'll talk about calculus of variations more later, which is super cool idea. Lagrange, way to go. Okay, so how do we do the proof now? There's a bit of a setup. Let me start over here because that space is, I'll go back over there in a second. So the setup then is that each of our surfaces m superscript t is given by, let's think of it as given by a graph, okay? So actually, before I draw this, let me draw the picture. So the picture is, we have an x and y axis here, and then a z axis here. And what I'm going to do is, it's actually kind of complicated to do a surface all at once, okay? So we're going to always try to simplify it. And this is the general principle of, is there an easier version of the problem I could study first? And you always do the easier version first. And there is, and that is, why don't we look at surfaces that are graphs, okay? So let's look at a surface that is the graph over, let's say, a rectangle, right? And then what we're going to do is we'll go ahead and have eta be 0 along the boundary, right? So eta equals 0 on the boundary of the rectangle, right? In fact, not only the boundary of the rectangle, but anything close to the boundary, right? So in other words, what we're going to do is we're going to have just a little bump flow the surface up just a little bump in the interior, okay? And see if we can compute the rate of change of the area of that. And since it's a graph, okay, so this is a graph, right, over this rectangle, that means that we can write it this way, right? We can say that our first original surface is just z equals some function of x comma y, right? That's a graph, right? So you have some function of x and y. Look at the graph of that. That describes a surface over that rectangle, let's say. And then what we want to do is, okay, well, how do we describe the surface at time t? Well, we'll call that z sub t. And what we'll do is, let's restrict to the case where it's something simple. We'll just add t times g of x comma y. And so that's telling us how the height is going to change, right? Like, how much are you increasing? Now, I could let this right-hand side be a function, just a function of x, y, and t. So what I've done is I've done a linear approximation. I really only care about the variation of m around 0. So in other words, I've sort of rigged it up to where it's a particularly simple case. Just make this depend on t, and then whatever the partial derivative of t is, that's what we call g of x comma y at t equal to 0, okay? So if we can solve this, okay, when we agree this is like the easiest variational problem, can you think of something easier? Right, like this, let's just try to make it as easy on us as possible. Can we solve this? Okay. And since we're looking at variations at t equal to 0, it turns out all that matters is the partial derivative of this graph is a function of t at t equal to 0, so without generality, we can just study this case. And then, we say, well, how do we compute stuff? Well, remember that we've done this before, right? That means there's a parameterization, x superscript t of u comma v. And so we plug into our pre-existing knowledge, right? Which is, okay, you parameterize a graph this way, right? Right, you just take your function there, right? And you just put it there as the z coordinate, right? It's a function of u and v. So that's the Monge patch stuff. You guys have done your homework already, I believe. And then you compute xu. You compute xv. Now there's the superscript t. That's the thing that's interesting, is that t is around 0, right? When t is 0, by the way, it's just our original graph, right? And you compute these things. And see, what is this? Partial derivative with respect to u is 1, 0, f sub u plus t g sub u. Is that right? And then this is, you guys better check me because I actually put a dot, dot, dot in my notes here. Okay, I just do it on the spot, which means I'm not copying off my notes here. Okay, the v derivative is this, and then we have an f sub v plus t g sub v, right? And then we always have to compute this next thing, right? xu cross xv, right? Now normally we're computing it, I have to put the superscript t here because everything depends on t. Okay? That's all that means. And when you do the cross product, by the way, we're having fun, right?
Oh, yeah.
Yeah, exactly right. I mean, in the sense that we're actually doing some work, right? Or maybe we're going to come up with something interesting. Okay, so what's the first entry? It's going to be, so we do the cross product. What I think of it is, I think of I, j, and k here, and that's the first row, it's the second row, and it's, okay, it's, this times this minus that times that, so I get a minus f u plus t g u, comma, and then I do the opposite here, it's this times this minus that times that, so I get a minus, oops, the whole thing was minus, right? You guys caught that, right? Okay, you're about to tell me, okay. I caught quick to, okay. All right. This times this minus that times that, so I have fv minus tgv. And then the last one is this times this minus that times that. That's a 1, right? Now, what is a of t? It turns out a of t is equal to the integral over this d here. Okay, d is this rectangle, okay? It's a graph over D. Graph over this disk D, right? Not a disk, this domain D. This is a rectangle as drawn. And it's integral of A of t is integral then over D. By the way, the book does double integral. Do you guys like to write the integral sign twice? Does that make you feel better? Okay, I'll do it. I'll humor you for a little while. Sometimes I may not, by the way. You see over here I didn't. Yeah, mathematicians, we don't do the double integral. We kind of think that's funny. Okay? It is a double integral, but it's a little redundant, so you just normally just do the one integral, right? Because what if I was integrating in a 17-dimensional space? Am I really going to do 17 of those things? Right? So when you go to general dimension, you generally just draw the integral sign once. I'll do it twice here just so you understand that. That's what the book does, right? So I'll use both a little bit. And then what you take the integral of is the length of xu t cross product xvt. And then du dv. Now, I don't know if you remember this formula from multivariable calculus, but that's a multivariable calculus formula. You guys recognize it? That's actually how you computed areas. Now, why is that? I'll tell you. Would you like to know? I'm going to remind you why your multivariable calculus that you're supposed to already know is true. It's because when you're looking at, and just draw that sort of picture again. Okay. This point is above this point, right? Well, actually, it's best to, let's draw it like this, okay? If I wanted to compute the area of this rectangle down low, I would simply add up the areas of all those tiny little rectangles, right? That's like a summation. Then we take the limit as delta x and delta y go to 0 and stuff like that, right? But if I wanted to know the area of this rectangle, I just add up the area of the tiny rectangle. Now each of these has lines up here, right? But they're curvy, right? Okay. Now, let's see here. So this point actually came from this. So imagine this point is directly above that point, okay? From my picture. Did I even have the same number of rows and columns? No, I didn't. I had 6 here, I had 5 there. Okay, anyway, you guys get the idea. Okay, you can pardon my imperfections here. Okay, this point's above that point. Okay, now xu, these lines are constant lines of, if I just increase u, right, this is technically the x-axis and that's the y-axis, but the point is, remember that, we had x equals u and y equals v, right? So if I increase u but hold v fixed, I'm going this way. That's sort of that direction, right? And so xu is in the direction of this curve. So that's xu is the 3-dimensional vector here, and then this is going in the v direction, and this right here is the direction of xv, right? And more generally, these are parallelograms up there, right? Because things can get all curvy, right? If I take very fine, xu and xv don't necessarily have to be perpendicular, right? They could have any angle between them. They could have any length. And that forms, and so in general, xu and xv forms a parallelogram up there, right? And to be more precise, really xu and xv are much longer than those things because those rectangles are getting very small. And so this is like epsilon times x v, and that's epsilon times xu. And these things have size epsilon down here. That's like epsilon by epsilon, right? And so if you look at the infinite summation, that's sort of like epsilon times epsilon there, okay? If I didn't have this term here, right? If I didn't have that term there, I would just be adding up the areas of the rectangles down below, and I would get the area of the rectangle in the xy plane. But that's not what I want. I want the area up here, right? Well, how much do areas get stretched by? They get stretched by exactly this factor here, right? Now, why is that? Well, because when you have, remember a parallelogram, the area of the parallelogram is the length of that cross that. And so maybe that's even a better way to do it is if you go epsilon here and epsilon there, then this is going to be epsilon xv here. And that's going to be epsilon xu here. And then this cross that, the epsilon squared factors out, that's the du dv. And then the xu cross xv is what's left. And remember, the area of this is just the length of that cross that. Take the limit as epsilon goes to 0. And that's the whole Riemann sum thing, right? Okay, is everybody convinced that's the correct formula? All right. And so then we can plug in here. And so then we get the integral over d of the length of this thing, which is the square root of 1 squared plus this squared plus that squared, right? Now let's just group the terms nicely. In terms of t, I'm going to get fu squared plus fv squared. Okay, notice I don't have any t's. And then plus, then I'm going to get the cross terms. When I square this and I square this, I'm going to get a 2t cross term in both cases, right? And let's see here, this times this, I get 2, this times this, so I'm going to get 2t times gu, fu gu. And then same thing here, I'm going to get fv gv. And then plus t squared times some stuff. Turns out that stuff doesn't even matter, so I'll just leave it like that, okay? But that stuff would be gu squared plus gv squared. And now what I want to do is, what we're trying to do, we're trying to compute a prime is 0, right? Ultimately, well, a prime is 0 is what we want. Because if we prove it for t equal to 0, we proved it for all t. Okay. Now you might say, wait a second, how come I can just ignore this term here? Well, if I wanted to do this, compute a prime of 1, then this would be relevant. Or a prime of anything other than 0, right? Would you guys agree that the slope of t squared is 0? So we'll just keep that in mind. But to first order, this isn't changing, t squared. Okay, so we'll see that it doesn't matter for a prime of 0. But then you're like, well, I thought you said t equals 0 wasn't anything special about it. Well, there isn't. But notice that these f's and g's are defined in terms of t equal to 0, right? At t equal to 0, f is what the graph is, and g is the partial derivative of the graph, right? So we're saying, look, I just want to do t equal to 0 by our setup of the problem, okay? F and g are meaningful at t equal to 0.
Did you write g sub t in there? Should that be g sub b?
Thank you. Yeah. Thank you, appreciate it.
Yep.
Okay. All right, so what is a prime of 0 equal to then? I would compute a prime of t and then set t equal to 0, but it's going to waste chalk, and I'm an environmentalist. And no, it's like, it just takes up a lot of space, right? We've got a limited amount of board space. But probably if I didn't have a clock on me right now, I probably would. I'd probably compute a prime of t and then let t equal to 0. Okay, so what is a prime of 0? Well, this is, by the way, not a partial derivative. It's a regular derivative in t. Single variable calculus is just a complicated expression, right? So what we have is the integral over d. By the way, I dropped my du dv here, didn't I? It's still there. I just forgot to put it in. I ran out of boards. Okay, so what is it? I remember my chain rule. I got the square root of something, which is something to the 1/2, right? So the way I do the chain rule is I have something to the 1/2. So therefore, it's 1/2 that something to the minus 1/2, and then times the derivative of that something. Okay. So I have something to the 1/2. So it's 1/2 that something to the minus 1/2 times the derivative of something. Well, what's the something? Well, something is all this stuff here. Okay. How about I just say stuff right now, okay? Okay? I actually do this. I actually do this, okay, in my actual computations. So I know what I mean. And then times the derivative of that stuff with respect to t, but then set t equal to 0. What's the derivative of this stuff with respect to t? Well, that doesn't have any t's in it, so it's 0, right? And then, So I get twice this, right? So I get 2 FUGU plus FVGV, right? And then plus 2t times that stuff, but then I want to set t equal to 0, so that's 0, right? 2t is 0, so 2t times anything will be 0. And then I have my du dv. And then I'll go ahead and put that stuff back in. What was the stuff here? Well, it looks like it's long, except when I set t equal to 0, then that term goes away and that term goes away. Right? And so actually it's just 1 plus fu squared plus fv squared when t equals 0. I didn't want to do that first because if, let me just say a common mistake in these computations is you set t equal to 0 and then take the derivative. Don't do that. You guys know not to do that, right? When you're computing this term, right, you have to take the derivative first, then set t equal to 0, right? If you have a function of t, and you set t equal to 0, and then take the derivative with respect to t, of course you're going to get 0, right? That's a rookie mistake, right? So if I'm computing f prime of t, f prime is 0, first you take the derivative, then you set t equal to 0. And in all the complexity, that's a pretty easy mistake to make, actually. Okay, so really compute a prime of t, write the whole thing out in its full glory. Probably should include this term here, right? And then set t equal to 0, and you see this is what you get. Okay? And so then what do we have here? Let's go ahead and simplify it. It's the integral over d. The 2 and the 1/2 cancel. I get this, not too bad fraction, FUGU plus FVGV divided by 1 plus FU squared plus GU squared to the 1/2, I think, and then du dv. And so we have an answer, don't we? We have an answer. But we're not done yet. Because we're trying to get this, okay? And first of all, we don't know what eta is. Right now, eta is kind of like g. Like eta here is the perpendicular flow, but over here, this g is not perpendicular flow, it's vertical flow, right? And so we got that difference. And the other thing, but that's a relatively minor difference. Is that in fact they're the same if your graph is exactly level at a point. They would be the same. The major difference is here there are no derivatives of the flow speed eta, but here the flow speed is like g, but we got derivatives of the flow speed here. And it turns out you can integrate by parts and get the derivative off of the g's. And that's where you get your insight. It's actually a much nicer form. This form is true, but what we're going to do is integrate by parts. Okay. Because when you integrate by parts, what you get then is technically it's also applying Green's theorem, but really you can think of it as integrating by parts. What you get then is this becomes remember you always get a negative sign when you integrate by parts? And what I want to do is take the derivatives off the g, right? And so what I'm going to do is, I'm going to do them one at a time. Let's do this term first. So ignore the FVGV. Just think of this divided by that, okay? So in other words, what I have is FU divided by this fraction, right? And I that times GU, right? That's what's multiplying times GU, right? So when I integrate by parts, the derivative on the G goes over to this thing, right? I get the minus sign, and then the G just factors out. Okay? That's integration by parts. You guys agree?
V squared instead of GU squared.
Oh, yeah. So I just randomly miscopied this. Thank you, I appreciate it. This was this, right? But I say it with confidence so you guys believe me, right? Let that be a lesson to you. And you like how I turn my mistakes into lessons for you guys? Yes, thank you. Yes.
So I know how to integrate by parts, but like in that context where you just made that simplification very quickly, could you explain that again?
Yeah. Okay, so integration by parts is that the integral, I mean, I'm right, is integral of u dv is equal to, some boundary conditions, right? Minus integral of v du. So there's one critical thing that I'm doing is, let's suppose that g, we're going to suppose that g is 0 on the boundary, okay? So I said eta is 0 on the boundary. In particular, I want g, right? So I want g to be equal to 0 on the boundary. That's actually kind of critical because when we integrate by parts, we get this boundary term, right, guys? And I'm saying I want that to be 0. The reason it's 0 is when we write integral of u dv equals integral of v du, the u, we're taking the derivative of the u, but we're sort of taking the antiderivative of the dv, right? And so in this setup, what we're doing is, just to be explicit, u is equal to, by the way, this u and v, I'm sorry, it's not the same as that u and v, all right? So capital U's and V's are over here, I guess. Sorry. Is that right? Okay. So the thing we're integrating by parts here, I mean, the u is this getting derivative, you're taking the derivative of is this. Okay. And then dv, this is the thing that we are effectively integrating, is gu. And so therefore that means our v is just going to be g, right? And so the boundary term, it's uv, which is this times that, but g is 0 on the boundary, right? We're supposing that we're not changing the height of the function on the boundary, right? We don't want a boundary term, I don't want to mess with it, okay? Keep things simple. And so the long and the short of it is, we're taking the derivative of that term, and we're integrating that term, making it a g. Because the integration, imagine it's a single variable calculus just in terms of u. I know it's a double integral, but in this case, I mean, a double integral is in fact two integrals, one in u, one in v, right? So if you just think of the integral in u, I can really think of it as integration by parts. Technically, because it's a double integral, we're using Green's theorem. If you want to get precise about it. Okay, it's also Green's theorem. You can think of it that way too. But it's also just integration by parts. Okay? And there's your minus sign. And then we'll do the same thing over here, right? The thing we're taking the derivative of, this time we're looking at it as an integral in v. So this is fv over 1 plus fu squared plus fv squared to the half. And then we're going to try to take that derivative. We're going to take the derivative of this term, right? So, great word work. Okay, exactly wrong. We're going to take the derivative of this thing. Okay, but we're taking the v derivative that was on g and put it on this thing instead, and then take it off gv, and now that just becomes g, and there's my minus sign from the integration by parts. Okay. Technically, we use Green's theorem there. By the way, the integration by parts, Green's theorem, same thing, actually. And so now we're like, oh, okay. All right. Now we had a formula for the mean curvature. What's that to the 3 times? Okay, so there's one last step, but we're almost there, by the way. This is almost like eta, right? And this right here, you're like, gosh, that's starting to look like the formula for the mean curvature. If I were to expand it out, right? And that's basically correct. We're basically done. The only difference is that oh, we have 2 more things to do, though. Let's add in one more line here. This G, it's almost like how fast you're flowing up, but not quite, right? I mean, it's not quite eta. What's the relationship between G and eta? And imagine you have, this is your graph right here, okay? This is my graph, okay? Graph of z equals f of x comma y, right? And I'm just trying to make it as straight as possible here for a second, all right? So you kind of have a triangle there, right? And so it's a triangle there to the you know, the more and more you do an approximation. And let's see here. Eta is the speed this way. And G is the speed this way. All right, so this is eta, and that's G. This angle here is the same as that angle there. All right, this is a right angle here. So, I mean, these are the complementary angles I'm marking twice, right? The angle 1 plus angle 2 adds up to 90. Okay? And so I've drawn similar triangles here. And if we think of this as 1, this right here is the length of the gradient of f. Right? That's the rate at which my function is increasing. Right? Imagine the gradient of f is going this way, right? This is how much things are tilted, right? Y'all remember that the gradient of f is it's the maximum rate of increase in the direction of increase, right? So I can think of this graph as coming out of the board here if I think of the gradient of f is going exactly in that direction. Okay. And by the rule of Pythagoras, it means this hypotenuse here is the square root of 1 plus the norm of the gradient of f squared. And so then by similar triangles, the point is that eta over g, the hypotenuse over the long side, is equal to the hypotenuse over the long side here. Okay, so eta and g are actually, they're off by a factor, right? And that factor is the square root of 1 plus norm grad f squared. Now, if your graph is exactly level, right? Yeah, the factor should be 1, right? If I'm exactly level, then perpendicular speed and vertical speed are the same thing. More generally, eta is equal to g divided by, whoops, there's a mistake in my notes here, sorry. Eta over g, oh, I got, eta over Okay. I decided to get clever and I didn't follow my notes and I outsmarted myself. Okay, but then why doesn't this work too? That's what I'm trying to figure out. Okay. I'm off by a reciprocal factor. Sorry guys. Oh. Okay. This picture is not the right picture, okay? I mean, let me draw the right picture, okay? It's just simply wrong. Okay, so let me draw the correct picture, and then I don't want to argue why that's wrong. Let me just argue why the correct picture is right, okay? If I go up with, let's pick this as our base point here, okay? If I go up with speed g here, okay, I'm going vertical, right? And then my speed is g, right? The question is, how fast are we actually moving perpendicularly when I go to this point right here? Well, at this point right here, what I have to do is drop a perpendicular, right? And so this is that's the actual correct picture. When I drop a perpendicular, when I go from here to here and then drop the perpendicular, I can see my perpendicular speed is eta. That's the correct picture. The picture I drew before, it was simply the wrong picture. Okay? Do we agree this is the right picture now? Okay. Because if I go up this much, this point goes to there, but how much, what's my actual perpendicular speed? Well, I need to drop a perpendicular to figure out what the actual perpendicular speed is. Okay.
So why is that vertical term the norm of the gradient?
Why is what?
The vertical one that you have is the norm of the gradient of f?
Oh, that's just, okay. So now this is just simply showing how much my graph is tilted, right?
Right.
And so
Oh, I guess it's
every time you go over 1, this is the speed of increase, right? You go over every time you go 1 in the direction of the gradient. That's how much you go up by definition, right?
Mm-hmm.
So the gradient of f is a vector. A vector is a direction and a magnitude, right?
Right.
Its direction is the direction of maximum increase, and its magnitude is the rate of increase in that direction.
Okay.
Okay. And then we see that so we're dropping a perpendicular. This picture here is it's perpendicular, but notice that this is vertical and that's horizontal. So these are complementary angles here. 1 plus 2 equals 1, and therefore this angle here is the same as that angle there. These are similar triangles. Okay. And so therefore, see what I wrote before is just simply wrong. So the adjacent, long side over hypotenuse equals long side over hypotenuse. The reciprocal of what I've written before. And so then this means that the actual speed eta is equal to g divided by the square root of 1 plus norm grad f squared. Okay. And so what I'm going to do here is I'm going to put a g divided by the square root of 1 plus norm grad f squared here, because then at the last step, that's going to be eta, isn't it? Okay? And then I have times this stuff in brackets here, okay? Which I'm not going to, I'll just say it like this, okay? By the way, see how I use brackets here and then I use brackets there? I just know everything that's inside the brackets. Right? So in other words, it matters that I use brackets and not parentheses or something like that, okay? But I want to do one other change too, by the way, which is what is dA, right? Well, remember, dA is the thing that you integrate, right? In fact, this is dA right here. But when dA is at t equal to 0, right? dA is the square root of 1 plus fu squared plus fv squared times du dv. Agreed? So one thing that comes out of this calculation is that dA at t equal to 0 is equal to the square root of 1 plus the norm of the gradient of f squared times du dv. Okay? Just plug in here. Remember, we were the AMT, this is the thing you integrate to get area. But when t equals 0, that term's not there, that term's not there. This is the norm. This is the norm of the gradient of f squared, right? And so that's what dA is. So I'm also going to put in the same factor over here. Okay? And then you look at this, you're like, oh, okay. This is therefore the integral over d of negative eta, there's the minus sign, this thing right here is eta, right? Times everything in the brackets there, times dA. Exercise. Everything in the brackets there is 2h. We're done. And when we computed it before, it was like a homework problem, right? I mean, it's going to be something. Look, whatever this is, obviously has geometric importance. Can we agree? So let's face it, look, if this didn't equal either k or h or something to do with k or h, it would be a new thing we would have to study, right? So maybe it's not terribly surprising. It's one of these important things, right? And you can kind of see, right, because we take the derivative, this 1/2 factor becomes a 3/2. We take a factor. Remember that was the h had this to the 3/2 in the denominator, right? And so just expand that all out using multivariable calculus. You get our formula for h. And we're done. Turns out you can make a living doing calculations like this. You have to do a little bit more than that, but actually being able to do computations is a limiting factor for many mathematicians, including myself. Probably for all of us, actually. I mean, never be too impressed with mathematicians. We all are extremely limited. It's just not quite as limited as everyone else sometimes. Like every once in a while we can do it. Like we actually get to the end and it's the right answer, right? And then so looking for new things to compute is, it's a great way to contribute as a mathematician, actually. I mean, this one is relatively. I mean, once you get good at it, you're like, oh, okay, this is a warm up. This was the easiest one, really, in many ways, right? But it's really not that easy the first time, is it? You just have to have patience. And then, so there you go. This is what mean curvature is. Okay, so we've understood mean curvature now a new way, and really a better way. Mean curvature is the first variation of area. Oh, by the way, a couple more details. I proved it for a graph now, but I haven't proved it for a surface, have I? And this is where you can start, you use the name calling. Any fool can see that. If it's true for a graph, it's therefore true for a surface. No. I mean, no, you can't do that. So technically, you say, okay, there's a gap here, right? But at this point, you're starting to get optimistic. Hey, I can prove it in the case of a graph. It's bound to be true for a surface in general. Bound to be, right? What else could it be, right? And technically, what you do is something called partitions of unity. And so what you do is, if I want to compute, and this is just the technicalities of it. This is not a very important. I mean, look, partition of unity, I guess, is a fundamental concept. Partition of unity. What you do is, see, here's the thing about it. Imagine our eta actually was 0 everywhere, except it was just a little bump function in one spot, right? Well, that one spot, if it's a graph, if you can represent that part of the surface as a graph, well, then we are done, right? Now, does it have to be a graph over the x-y axis, or could it be a graph over the y-z axis just as well? Yeah, it doesn't really matter. It could be the graph over any two axes you like. In fact, you can even rotate the thing. It doesn't change area, right? So all you need is that with respect to some rotation, you can make it a graph locally, right? So the key point is, what I do is, What is a partition of unity? I say 1, which is defined on the surface, right, is equal to the summation k equals 1 to some capital N of, what function do we want to use here? All right, so we've already used f and g. I mean, we could do h. I mean, if it's a partition of unity, I was thinking about u, but we've already used u, right?
Omega.
Bump function, b. B for bump function. There we go. Okay, thank you. You guys helped me brainstorm that out. B sub k.
What's a bump function?
A bump function is a function that looks like a bump.
Oh, nice.
All right.
That's great.
Yep. And so what we're going to do is, like, the real point is the bump function is 0. I mean, sometimes bump functions decay exponentially, but we want bump functions that are exactly 0 here and exactly 0 there, okay? They have a finite, they have what's called a compact support, right? So there's basically 0 everywhere except on this bounded region, right? And the point is, if I have a bunch of bump functions, I add them up, right? If I add up a bunch of bump functions, they add up to, guess what? I can choose where they add up to 1. You guys get the idea? So to choose a bunch of bump functions, see a point on M, what we're calling that P, right? For all P contained on M. Okay? So what we're going to do is, we're going to find a bunch of bump functions such that when you add them up, you get 1. You get the idea? Now, how do you do that? Exercise. Standard exercise. So, you know, how about this? I would just take a bunch of bump functions. They're going to add up to something, right? Make sure it's not 0 anywhere, and then just normalize. In other words, divide them all by what that sum is. Now they all add up to 1. Right? Okay, so not too bad. And furthermore, choose them to be smooth and nice and everything. And so we have these smooth functions that add up to 1. Okay, and then what you do is you say, well, I'm computing a prime of 0. For some function eta, and then we're going to just use the fact that I can multiply this through by eta, and so what I get is eta is equal to the summation k equals 1 to the number of bump functions n of eta b sub k of p. Okay? And so and then what I do is I just do the variation for each of these. So a prime of 0 for eta, okay, is equal to just add up the rate of changes of a prime for each of these individual things, eta times b sub k. And each of these, so the fact that this is the sum of that is just because it's linear in my flow speed, right? So if I have this variation plus that variation, the derivative of the sum is the sum of the two derivatives. So just by linearity in my flow speed, I can do this, but each of these is a graph. So we're done. We proved that over there. You'll see partitions of unity. It's just a fundamental concept in this, you know. And so because of partitions of unity, this is what allows us to say, oh, wait a second. If we can just prove this in the graph case, then we can prove it in all cases. Questions?
Push.
Can you say? I'm slightly confused what we just proved, like in like English terms, like intuitively.
Sure. Okay. Let me compare the formula we just proved here in the box
Yeah.
to the formula that's easier for you all to understand, which is v prime is 0 is equal to the integral over m0, right? Or our surface m. I mean m0 we call m, right? m0 we can just call m, right? Okay, so integral over m. So the instantaneous rate of change of the volume is just eta times dA.
Yeah.
Okay. And I really do like compare these formulas because they're the same except for this factor here, minus 2h, right? And so really it is true. Like, here's what's really true. If you wanted to measure the mean curvature of something, and all you could do were volumes and areas, right? What you could do is, if I want to know what the mean, I mean, here I have a flow right here. This is kind of saying, a way of sort of testing, let me draw a picture. If I have a surface and I want to know what the mean curvature of this point is, I could just do a flow like this, where you're flowing 0 everywhere except around that point.
Yeah.
And I could, if I compute A prime as 0 and then divide that by B prime as 0, it's going to give me some sort of average of the mean curvature. It's a way of measuring the mean curvature at that point. 2h, negative 2h will pop out. Okay? By the way, another thing we should do is check that this actually works. Okay? With an example. And one example, remember, unfortunately I erased it, but when you have a sphere, right? The mean curvature was negative 2 over r, right? Where r is the radius. And and we know that the area is 4 pi r squared, right? That's correct, right? And then, look, basic calculus, A prime. What's the rate of change of the area, right? A prime of r, right? That's going to be 8 pi r. Am I right? 8 pi r? Just calculus, single variable calculus. By the way, which is equal to the integral of something of area of 4 pi r squared of 2 over r dA, right? Because if I integrate 2 over r of something with area of 4 pi r squared, just multiply, I'm going to get 8 pi r, right? And so it checks out in this case. Okay. That the mean curvature, so, whoops, I think you're pointing out a mistake.
No.
Okay, there's a mistake right here. Mean curvature is this, right? And so that's minus 2h there. Okay. Sorry, I just got confused with the conventions for a second. So the mean curvature is this, minus 2h is 2 over r. And so we see that it works for a sphere. Do you guys see that? If my flow speed is 1, right? Then eta is 1, minus 2h is 2 over r. And sure enough, the integral of 2 over r dA is in fact 8 pi r, which is the rate of change of the area. And so that's the first example we should always do, right? Now what's another example? So you have a plane, and you just move it. Let's say you have part of a plane, you just, see, so far we've only done surfaces that don't have boundary and go off to infinity, things like this, right? But if you have a plane, you move it out, the area doesn't change at all, right? Mean curvature is 0, so that kind of sort of checks with our examples.
Is that true for all minimal surfaces?
Yeah. In fact, h equals 0 is the definition of a minimal surface, yep.
Right.
And since h equals 0, to first order anyway, the area does not change.
Will we find that that's true for higher orders too?
No. So, yeah, this is just a first variation. Guys, guess what? There's a second variational formula.
Oh, no.
Even more fun. The first variational formula, everybody can do that. The second variation formula, I actually have made a living off. My early work as a graduate student was just expertly applying the second variation of area formula in ways that hadn't been done before to black holes. And hey, here's your PhD. Okay. I mean, I'm not exaggerating. That's somewhat accurate. So look, it's not that complicated, the second variation of area formula. We're not going to do it in this class. But it gets, to just take the complexity here and multiply by 5 or something, then you got your second variation of area formula. Okay?
I guess I'm realizing it makes sense that the minimal surface satisfies that condition, because that would mean that there would be a direction that you could kind of move it, and then the area would get smaller, which is contrary to the definition of the minimal surface.
Yeah, exactly, right? So what was your name again?
Ray.
Ray. So what Ray just said is, like, if the mean curvature wasn't 0 for a if you're like a soap film, right, and you're locally minimizing area, if this isn't 0, then there exists an eta such that you can just to first order make the area smaller. Right, or bigger, your choice, right? Whatever you want to do. And by the way, a second, if it's really truly locally minimizing area, that shouldn't be possible. Right? It shouldn't be possible to make the area smaller locally. Yeah, exactly. And this brings us to the whole calculus of variations things about soap bubbles, which is super cool. I mean, calculus of variations is a big topic. It's actually super cool. Let me show you all, first of all, the simplest example of calculus of variations. I love calculus of variations, but imagine you have the xy plane here, right? And I guess, let's say you have a disk of radius 1, and I say that, look, I want my function f of x comma y to equal, let's say it equals x plus 2y, on the boundary, right? On the circle. Okay? But I'm not saying what my function of x comma y is inside the circle. It could be anything, okay? But it equals x plus 2y on the circle. And then I can say, problem, find the f of x comma y, which minimizes e equal to the integral over this disk of the norm of the gradient of f squared dx dy. In other words, you know how calculus is about maximization and minimization, optimization, right? They give you a function, they say find a local max, find a local min, right? That was single variable calculus. Multivariable calculus is you had a function of multiple variables. Find a local max, find a local min, right? Calculus of variation takes it one step further. I didn't say find the point x comma y that maximizes some function. I said find the function that maximizes some functional, e. E is like the functional, right? So this is like e of a function, right? You give it a function, and it gives you a number out. Find the function that minimizes something. All right, that's new, isn't it? You haven't done that before, probably. That's calculus of variations. In other words, give me the best function. What's the best function? It's the function that minimizes that functional. Now, why would someone want to do this? Well, I might say, you know what? Don't give me some curvy function that's unnecessarily wavy, right? Like let's just try to have it. In other words, if you give me a look, if the boundary condition was f of x comma y equals 1, I'd just say fill in with 1 everywhere, right? Just go ahead and make it a constant function. If it's constant on the boundary, make it constant in the middle. That's the nicest solution, right? And this is saying, okay, make it as constant as you can. Right? Make the gradient of f, make it as close to 0 as you can everywhere, but sort of on average. Now, is there anything holy about this functional? No, you can choose any functional you want, depending on your application. Give me the best function, f of x comma y. That's what calculus of variations is all about. Okay? And it turns out we can solve it using techniques very similar to what we just did. Because this is equal to the integral over d. Well, actually, so this is how you do it. So the general, this is your problem. Okay, so now, solution. You say, suppose we have a solution, okay? Suppose f of x comma y minimizes. So by the way, the fact that we're supposing you can minimize it is already an assumption, okay? We haven't proved that. Let's suppose, but suppose there was a minimizer. Maybe there won't be a minimizer. You guys know the functions like if y equals 1 over x, and you say minimize for x greater than 0, well, the solution is at x equal to infinity, right? It's like there is no solution actually, right? But anyway, suppose there was a function, f of x comma y minimizes. And then for all g of x comma y, we're going to do the same thing we did last time. If we let f sub t of x comma y equal f of x comma y plus t g of x comma y. Now see what we're doing? We're doing the same thing as we did before, right? We're taking our f and we're adding t times g to it, right? then it must be true then it must be true that when we do our graph, right, and we say this is t, and we look at E of t, now what's E sub t? E sub t is just the energy of this function, right? Must look something like this. It must be a local min at t equal to 0. Okay, must be minimized, right? Minimized at t equal to 0. You guys agree? I mean, look, if we had a true minimizer, then when we vary it with any other, so this g of x is the variation, right? So then we get one parameter family of functions, right? T goes between, minus infinity, infinity, whatever. But when we graph it as a function of t, the energy, right? We call this E energy, right? Then the point is you must have a local min at t equal to 0. Agree? Which means the slope there is 0. No? That's an equation we can write down. So the point is that 0 must equal d dt of this E sub t at t equal to 0. In other words, when we take d dt of this thing, the integral over d of the norm of the gradient of f plus tg, right? Squared dx dy. And then plug in t equal to 0. That must be 0. Okay, well what does that mean? We do the calculus, take d dt of this. Now by the way, take d dt, then plug in t equal to 0. If you plug in t equal to 0 first, it's not a function of t, take d dt of it, you get 0. That's not even true, right? What this means is take d dt, right? First take the derivative with t, then you plug in t equal to 0. Which is obvious when I point it out, but that's a common mistake to make algebraically because it's always so complex and it's just sometimes you lose track of what you're doing. Okay, so you take d dt of this, we get the integral over d. What is the norm of the gradient squared? Let me use the fact that the norm of a vector squared is equal to that vector dot product itself. The vector dot product itself. And the reason that's nice, when you see this, think that, right? Because then I can use the product rule. Okay? And so then what I get then is I get 2, the gradient of f plus tg dot product the gradient of tg. Excuse me, g dx dy. Okay, so this is norm v squared. This is the v dot v, and what this is 2 v dot v prime. Okay. You guys understand? So I have 2. The 2 comes. Effectively, it's like something squared, right? But another way to think of it, it's v dot v, so it's going to be v dot v prime plus v prime dot v. So I get 2 v dot v prime. So it's going to be twice this vector dot product the derivative of the vector respect to t. Derivative respect to t is just the g. Okay. And then I want to do this at t equal to 0. And so that means what I get then is the integral of, take the 2 out, integral over d of the gradient of f, because t equals 0, dot product the gradient of g, dx dy. This equals 0 for all g. For all g. No matter what g I choose, right, I'm going to get this a local minimum. This is true for all g. That's a very incredible statement. Think about it. This integral is 0. No matter what g I choose, somehow or another, magically, this must be 0. How could that possibly be? Well, so far it's not obvious what to do with this until you iterate by parts. Because when you iterate by parts, or use the Green's theorem, or actually the divergence theorem is what we're using here. And what we're going to do is, let's go ahead and assume that g is 0 away from the boundary, so there's no boundary term, okay? Let's go ahead and have g equal to 0 away from the boundary. So when I integrate by parts or use the divergence theorem, there isn't any boundary term. Then I get minus 2, the integral over d, and then I have Laplacian of f. That's the divergence of the gradient times g dx dy. And now when I say, so what is Laplacian f? It's the divergence of the gradient. Okay, this right here, that is the divergence of the gradient of f. Okay, also known as the Laplacian. And by the way, if you write that out, that is just fxx plus fyy. Okay. And so when I say that the integral, so there's a minus 2 here, this has to equal 0 no matter what. How is it possible that the integral of this expression times g equals 0 no matter what g is? Oh, now I see. It must be that the Laplacian of f is 0 everywhere. If the Laplacian f is 0, anything times 0 is 0, right? Doesn't matter what g is. In fact, that's the case. It must be the case. Otherwise, if this isn't 0, I could choose g equal to that, right? And then I would get something that's not going to be 0. Integral of anything squared is not going to be 0 unless it's 0 itself point-wise. And so this implies then that f, to answer to my original question, is I need 0 to equal the Laplacian of f. That's ffx plus fyy. So in other words, if I can find a function whose Laplacian is 0, it's the answer. Oh, actually, guess what? So the answer is in the boundary problem. You just extend f of x comma y, it's x plus 2y. You'll see that take 2 derivatives with respect to x, you get 0. 2 derivatives with respect to y, you get 0. So in fact, the function on the interior is also just x plus 2y. Now, more generally, if I'd given you more complicated boundary data, what the answer in the middle wouldn't seem to have anything to do with the boundary, right? It would just be the function that satisfies this with those boundary conditions. These are called harmonic functions. And harmonic functions, which, I'm sure they are very important functions, and I like harmonics and music and stuff like that, and it kind of suggests there's something to do with music, and there sort of vaguely is, but it's just a name. And so that's probably the standard example of calculus of variations, or be harmonic functions. They're functions that locally minimize this energy functional. And you can do the same thing, by the way, with surface area. You can say, here, we said find the function with certain constraints on the boundary which minimizes something. But over here, what you might say is find the soap bubble which has to enclose a certain volume V which minimizes total surface area. Well, technically, that's a calculus of variations problem too. So the soap bubble problem is also a calculus of variations problem. And then you can, because you put a, because it's not like it's minimizing something, but that something isn't, you're not just choosing an x value of a function to minimize, right? You're choosing, you're putting a function in and getting a number out. Here we're taking a surface in and getting a number out, right? And so this is calculus of variations to minimize surface area of a soap bubble. And when you do the calculation, what turns out is we've already done the hard work of the calculus of variations of that soap bubble problem. Because we can use this formula right here. And it turns out that if this thing minimizes surface area, it turns out it must have constant mean curvature. And let me just draw a picture to convince you of this. I'll erase this right here. And basically, the argument comes down to this. Let me prove to you that this is not a soap bubble. Okay, you can say, wait a second, that's clearly not going to work out, right? Well, let me prove to you I can decrease the surface area of that. And preserve the volume, right? Because all I have to do is I'm going to flow in here and out there, right? And the point is that you all see that the area is going to decrease faster here because the mean curvature is larger there, and the mean curvature is smaller here. So so if I do it equally, the volume won't change, but the area will decrease more here than it will increase there, right? And so if you're a soap bubble and you which locally minimizes area with a volume constraint because there's trapped air inside. The point is, I have to have the mean curvature equal to a constant. just like I have to have velocity of this equals 0, the analogy is over here, I get a second order equation too. We did it, we integrated by parts, all that. This H has FUUs and FEVs in it, right? And the point is that that's what has to equal, well, not 0 in this case, it has to equal a constant. And if you're a soap film, and I said, hey, here's a bent metal wire, and I dip it in soap, then that soap film has to choose H equals 0, which would be analogous to this equaling 0. And then with the volume constraint, it has to be a constant, because if I go in here, I have to go out somewhere else, right? So all I can say is the mean curvature has to be the same everywhere. And in the book, they show you an argument that H equal a constant implies a sphere. And there's some, that's actually kind of hard to do, by the way. To show that when H is constant, it must be a sphere. But it's true, it's in the book. I refer you to it. That's just straight geometry. Okay, good to see you guys. Good luck on your homework. And I'll see y'all next week. And don't forget, we have a test coming up a week from today. So, I would probably get your review sheet done this weekend. Why not? And by the way, you don't have homework due next week, you have a test. So the idea is, it's not to take time off, it's to allow you to study for the test.
Right.
That was the logic, okay?